For 15 years, scientists told us this snake proved the Earth was hotter than we ever imagined. They were wrong, or at least not entirely right. In 1994, a Colombian mine worker found what he thought was a piece of petrified wood. He put it in a display case. He walked past it every day for 9 years. It wasn't wood. It was the first bone of the largest snake that has ever existed, and what scientists built on top of that bone would spark one of the strangest fights in modern paleontology, a fight that's still not fully settled. This isn't the Titanoboa video you've already seen. Stick around, because by the end, the hottest place on Earth claim you've probably heard a dozen times is going to look a lot shakier than you think. Northeastern Colombia, La Guaira province. Today it's one of the largest open-pit coal mines on the planet, a vast dry orange scar in the Earth. 60 million years ago, it was something almost unrecognizable. A hot, swampy, equatorial rainforest crossed by wide, slow rivers, sitting less than 10 million years after an asteroid ended the age of dinosaurs. The mine exposes rock in a way the surrounding jungle never could. Tropical forests are terrible for fossil hunting. Everything is buried under meters of soil and root systems. But an active coal operation strips all of that away, layer by layer, exposing sediment that hasn't seen sunlight in tens of millions of years. That's what made valuable to science long before anyone knew a giant snake was waiting inside it. The first clue came in 1994. A local geologist working at the mine, Henry Garcia, found something he assumed was a fossilized branch. It looked woody, cylindrical, unremarkable. He put it in a display case in the coal company's office, where it's at, misidentified, for 9 years. Nobody was looking for a giant snake. The team that eventually formed at was chasing something else entirely. Plants. In 2003, a geology student named Fabiani Herrera found beautifully preserved fossil leaves in the mine, direct evidence of what this Paleocene rainforest actually looked like. That discovery pulled in Carlos Jaramillo, a paleobotanist with the Smithsonian Tropical Research Institute, and eventually Scott Wing, a Smithsonian expert on Paleocene-era plants. It was Wing who took a photograph of that supposed petrified branch sitting in the office and sent it to a paleontologist in Florida named Jonathan Block. Block's first reaction wasn't excitement, it was disbelief. He looked at the photo and thought, this can't be a snake vertebra. The proportions made no sense. He later described the feeling as being handed the skull of a mouse the size of a rhinoceros and being told calmly that it was a mouse. It's just not possible. That was his exact thought. But it was possible. And what happened next is the part almost nobody tells you. It wasn't a senior scientist who confirmed it first. Back in Gainesville, Florida, thousands of individual fossil fragments were being sorted, catalogued, and compared. It was 2 University of Florida graduate students, Alex Hastings and Jason Bourque, who were the first to recognize that the strange vertebrae belonged to an enormous, previously unknown snake. Not Block, not a famous name. 2 students doing the unglamorous work of sorting boxes of rock. Once that recognition happened, Block needed someone who actually specialized in fossil snakes, and there weren't many options. He reached out to an old colleague named Jason Head, a paleontologist who, by his own field's admission, was one of a small handful of people on Earth with deep expertise in serpent fossils specifically. Head would later describe the animal's width with a joke that stuck. If this snake decided to come through his office door, he said, it would literally have to squeeze to fit. Between 2003 and roughly 2007, the team quietly built one of the strangest fossil collections in paleontology. More than 180 individual bone fragments, eventually traced back to at least 28 separate individual snakes. Not one lucky skeleton, 28. That number matters, because it meant this wasn't a freak outlier, a single monstrously oversized individual. This was a population, a species that regularly grew to this size. And yet for years they had almost no idea what its head looked like. Snake skulls are fragile, loosely connected, and almost never survive fossilization intact. The team had a spine, they didn't have a face. Using the vertebrae alone, Head worked with Indiana University paleontologist David Polly to estimate body size by comparing the fossil vertebrae to the vertebrae of living giant snakes like anacondas and boas. Their math produced numbers that sounded almost fictional. A snake roughly 12.8 to 13 meters long, over 40 feet, weighing somewhere near 1,135 kilograms, more than a full-grown rhinoceros. In 2009, the species was formally named and published in the journal Nature, Titanoboa cerrejonensis, titanic boa constrictor of. But naming it wasn't the headline that made the science world argue. What made scientists argue was a second claim buried in the same paper, one about the temperature of the ancient Earth itself. If you're into prehistoric stories built entirely from verified science, not recycled Wikipedia facts, this is exactly the kind of deep dive we do every week on this channel. Every claim in this video is checked against multiple independent sources before it goes in a script. Subscribe if that's the kind of accuracy you want in your feed, because what comes next is where the story gets genuinely contested. Here's the logic Head's team used, and it's clever enough to deserve explaining properly. Snakes are ectotherms, cold-blooded. Their body temperature depends almost entirely on their environment, and there's a well-documented relationship in cold-blooded animals. Metabolic rate slows down as body size increases, meaning a huge ectotherm needs a warmer environment just to keep its metabolism running at all. Scale that relationship up to a snake the size of Titanoboa, and Head's team calculated that the mean annual temperature of the Paleocene tropics would have needed to sit somewhere around 30 to 34 degrees Celsius, several degrees hotter than most previous estimates for that era. It was a bold claim. Essentially, this snake's own body is a fossil thermometer for the entire ancient equator, and within the same year, in the same journal, 3 separate teams of scientists published direct rebuttals. Paleoclimatologist Cale Snyderman pointed out a problem with the underlying assumption itself. Using an ancient temperate zone lizard as a counterexample, he showed that applying Head's model consistently would predict that living tropical lizards should be capable of growing over 30 feet long. They obviously aren't. A team led by Anastasia Makareva argued the math needed serious recalibration, suggesting the actual estimate should be adjusted downward. But the sharpest challenge came from Stanford biomechanics specialist Mark Denny. Denny argued the entire logic was backwards. An animal the size of Titanoboa, he pointed out, generates a meaningful amount of metabolic heat purely from its own enormous mass, a phenomenon called thermal inertia. If you account for that self-generated heat, Denny calculated, the actual ambient temperature needed to have been 4 to 6 degrees cooler than Head's team proposed, or the snake would have been at risk of overheating rather than needing extra warmth. Head and his co-authors Block, Polly, and Jaramillo published a formal reply defending their core method. They stood by the underlying model and pointed out it held up when tested against the largest living snake species, the reticulated python. But even in that defense, they acknowledged something notable: their original temperature estimate may have run a little high. That's the part of this story almost never gets told in Titanoboa content. This wasn't scientists discovering a fact and everyone nodding along. This was a real, published, multi-year disagreement about whether one snake's fossilized spine can actually tell us the temperature of the entire ancient world, and it still isn't fully resolved. Later work, including a 2023 paper examining anaconda biology for comparison, kept pushing back on how much behavioral heat regulation a snake this size could manage on its own, which would undercut using it as a precise thermometer at all. So when you hear Titanoboa proves the Paleocene tropics were the hottest they've ever been, that's not settled science. That's one hypothesis in an active, unresolved argument, while that debate played out in journals, fieldwork kept going, and in 2011, 2 full years after Titanoboa had already been named and become a museum sensation, the team finally recovered something they'd almost given up hoping for: pieces of an actual skull. It wasn't beautiful. Block himself admitted as much, but it was a snake skull, and complete snake skulls barely exist in the fossil record at all. What it confirmed mattered enormously. The jaw and tooth structure matched a true constrictor, closely related to modern boas rather than 2 venomous snakes. Titanoboa killed the way an anaconda kills today, coiling, applying pressure, cutting off blood flow, then swallowing prey whole through a jaw capable of disarticulating to fit meals far wider than its own head. Some estimates suggest prey up to roughly half the snake's own body mass. And that raises an obvious question: what was it actually eating? Here's where the story usually goes wrong in other videos. People imagine Titanoboa hunting mammals because that's the default image of a post-dinosaur predator. But right after the extinction event, mammals were still small, mostly rodent-sized, mostly under 10 pounds. There was nothing walking around that could feed an animal. Weighing over 1,000 kilograms, Titanoboa's real world wasn't a mammal world, it was a reptile world, and turned out to be full of them. Alongside Titanoboa, the mine has produced fossils of at least 3 distinct crocodile relatives: Acherontosuchus, slender-snouted and up to roughly 6 meters long; Anthracosuchus, broader-headed and more heavily built; and Cerrejonosuchus improcerus, small, only 6 to 7 feet long, its name literally translating to small crocodile. From researchers who described that species said outright that its size made it easy prey, and pointed to a modern parallel. Anacondas today are documented eating caimans. Fossils of Titanoboa and Cerrejonosuchus are frequently found close together in the same layers. Then there are the turtles. Carbonimes cophrenia, freshwater turtle the size of a small car, the largest freshwater turtle known from the Paleocene, and Puentames mushazensis, arguably the strangest of the group, a shell nearly 5 feet across and almost perfectly circular, closer to a tire than a typical turtle shape, researchers. Studying it suggested the round shape may have maximized surface area for sun exposure, part of a broader pattern of tropical reptiles ballooning in size once the dinosaurs' ecological pressure disappeared. Some of these turtles show bite marks consistent with attacks from the crocodilians sharing their swamp evidence of a food web, where nearly everything large enough to matter was a reptile, both predator and prey. That's the actual picture. Paints, not one giant snake in isolation. An entire ecosystem of monsters built in the 10-million-year window right after the dinosaurs vanished, when reptiles not mammals briefly inherited the record books. So where does that leave the hottest Earth ever headline? Somewhere in between certainty and myth, Titanoboa's sheer existence does tell us something real. The Paleocene tropics supported an ectotherm larger than any snake alive today, which means conditions were, at minimum, warm and stable enough to sustain that kind of growth over millions of years. That part isn't seriously disputed. What is disputed is the precision of the number attached to it, the confident 32-34 degrees Celsius that gets repeated in headlines and documentaries as if it were as solid as the fossil itself. In reality, it's the output of a contested model, challenged by multiple independent research teams, defended but partially, walked back by its original authors, and still being tested more than a decade later. That gap between what a single fossil can prove and what gets claimed in its name is the real story most Titanoboa content skips entirely. It's easier to say science proved the Earth was an oven. It's harder and more honest to say one enormous snake gave scientists a genuine clue, and then scientists spent over a decade arguing about how far that clue could actually be trusted. There's one more detail worth leaving you with. In 2011, a team of engineers led by Charlie Brinson didn't just study Titanoboa, they rebuilt it. A working hydraulic robot, 10 meters long, 20 aluminum vertebrae, 40 hydraulic cylinders driving its movement, with plans to eventually extend it toward the snake's estimated full length of nearly 15 meters. It's a strange footnote, but it captures something true about this whole story. Titanoboa has always pulled people toward extremes, toward the biggest claim, the biggest number, the biggest reconstruction. The actual science, as usual, is more careful, more contested, and more interesting than the headline ever let on. We weren't completely wrong about Titanoboa. We were wrong about how certain we were allowed to be.